I'm not sure if you can see this clearly. Hopefully you can see it clearly. Okay, this is actually a previous, maybe not very clear, yeah. Okay, can you see the screen?
Yes, madam.
Okay, so this is one of the examples. Actually, it's already in the Moodle. You can just also downloaded it. It's actually previous SEM's question, not previous SEM, I think last year's SEM 2, yeah, SEM 2. So normally for the test, we have two questions, one chapter 2 and one chapter 3. So normally this is one of the good example, I mean not good example, one of the example of the question for the test. You have chapter 2 question. You can see that you have the single degree of freedom system, and you are asked to find maybe the EOM. In this case, you are lucky, they give you the EOM. You just need to find the K equivalent and the C equivalent. And then you have to find the conditions. Under those conditions, you need to solve the problem. Yeah? I give you overview first. At the same time, in this case, they give you the response of the system. So kat sini. So this one, that means you need to use your equation, okay, in order to find your, using your logarithmic decrement. So you need to know how to do that. And then the second question is chapter 3. Okay, move up it a little bit and blow this out. So in chapter, in chapter 3, you have this problem. Okay, you can see that is one of the famous system is our bar problem. Okay, so we're still talking about single degree of freedom system. In this case, it's a rotational system. So as I said, you need to make sure how you know which equation to use. Same equation, but now your EOM. Here also you are lucky, they give you the general equation, EOM. So you, when you actually derive, you just need to get what are the values of your J naught and so on. And here they also give you J naught straight. Remember, please check the notes in the video as well. We already derived for different type of J naught. Okay, J naught is the moment of inertia based on the axis of rotation naught or 0 O. Okay, if your J at center of gravity, for example, mass of a bar, okay, J at center of gravity does not coincide with your axis O, pivot axis O, then you need to use the parallel axis theorem, which is J at the center of gravity plus MD square. Okay, parallel axis theorem. I give you an example in the previous lecture as well. Yeah, how you do that. Okay, maybe we just go a little bit detail on that problem. Chapter. We take a look at this problem first. Okay. All right. So we take a look at this problem first. Yeah. So we have this single degree of freedom system. So they give you the equation. So this one is easy peasy. Yeah. So you can see that the information or background in chapter 1 is very important because you actually need to find the equivalent K and equivalent C here. So if it's what do you do to find your K equivalent and C equivalent class in this case? What do you do if your K is in parallel? What is your K equivalent?
Just add K1
Yeah.
K2.
So very easy, isn't it? So your K equivalent is just equals to K1 plus K2. Yeah. And your C equivalent here, because it's in series, so don't just add them up. You have to take the inverse of that, which is equals to 1C1 plus 1C2. All right. So if you rearrange that, you should get your C equivalent is C1 plus, well, it moves. C2, now I cannot write on this. C1, C2 plus C1 plus C2. So you basically you answer part A there. Okay. Take note that if you have two questions, of course, the marks going to be a bit large there. Okay. They just want you to write on the K equivalent and C equivalent. Then part B, you want to compute the system's undamped natural frequency, critical damping coefficient. Okay, so if you look at that, what you want to find? What is undamped natural frequency? So part B basically, let me just do it a little bit. Next to this, it'll be easy. So part B, then you would need to calculate on the undamped natural frequency. Yeah, so you have the omega n, which is equals to whatever that you have calculated for your K equivalent divided by M. So that'd be easy, isn't it? So they give you the values here. So basically your K equivalent from A, if you look at your K equivalent, what would be your K equivalent class? You just add them up, isn't it? 200 plus 400, correct? What is your M? Class?
20.
20. Yeah. So your M is 20. So if you calculate that, you get 5.477. So that is easy. Okay, then you calculate your critical damping coefficient. Okay. What is critical damping coefficient? Is it C or CC? Plus? Yeah, critical damping is CC. Okay, damping coefficient is C. So you do have the equation 2m omega n. So you can calculate your m is 20, your omega n, you can calculate that. So if you substitute, you get 219.08. Okay. And then you have to calculate your damping ratio. Okay, and damp natural frequency. Okay, so how do you calculate your damping ratio? You take a look at the list of equation. You have your C equivalent divided by CC. So your C equivalent is basically in, you have to compute the value from if you substitute the value, your C equivalent should be 36. So you would have, if you calculate 36 divided by 219.08, so you will get 0.164. Okay, and then you have to calculate your omega D. So you have your omega n, you have your zeta. So you can use this formula. So if you calculate that, you can get 5.403 second. Okay, the part C. Sorry, I have class until 11. Until 12. So the C determine the position of X of the mass at T equals to 6. So you have your, in this case, if you remember your XT, okay, which equation do you use in this case class? If you look at your list of equation, how do you determine which equation you use? What is your zeta value? What is your zeta value?
So it should be under that.
Yes, because your zeta is less than 1, which is 0.164. So you have to look at for the underdamped equation. So if you look at your underdamped equation, you have to compute your A. Okay, because they give to you already initial displacement. So what is that? Your x naught. Okay, if you refer to your equation. So also very important to take note that all the units will be in standard units. So your x naught is the initial displacement, and then you have your v naught is your your initial velocity here, which is 0.04 meter per second. So if you look at your list of equation, you have that A, you substitute, you should get 0.008. So use for the underdamped. Okay. Then once you get your A, you need to get your phi. So if you substitute the value, your phi is 0.253. Okay, I don't show the overall. You can check back the solutions. It's already in Moodle. I just show you the basic steps, yeah? How you're gonna do this. So when you actually, because they want you to substitute now, t equals to 0.6 seconds. So you have to substitute into your xt equation, which you get it from the list of equation with your A. Because you already calculate your A using the equation. You have your zeta, your omega n. So you have to substitute everything. And your t will be at 6 seconds, 0.6, yeah, 0.6 second. So then you have your sine omega dt plus phi. Okay, so it's all about substituting, and then you should get negative 0.0016 meter. All right. Any questions so far? If not, we go to part D. Okay, now damper C, it says here, part D, damper C is now removed from the system and replaced with another damper with an unknown coefficient C3. Okay, so they are referring that what they do is C1 is going to be changed with C3. Measurement of the free vibration response of a system is figure 2. Estimate the value of C3. In other words, now we are referring to this figure. Okay, so this is also very important where you need to, oops, let me blow that up a little bit. There. Okay. All right, so for this figure, okay, how do you actually calculate if you replace C1 with C3? That's what it says. So you have this response. What they want to do is you need to use the logarithmic decrement equation. So you have your logarithmic decrement. If you look at your list of equation, 1 over n ln. Okay, what is x1 and what is xn plus 1? Okay, remember n is the number of cycles. Okay, how many cycles you see here? Okay, this is maybe I blow it up a little bit. This is your point here. Yeah. So you can see how many peaks here. If I label, okay, maybe this is x1, x2, the points, yeah, x3, x4. Okay. So you have 4 peaks, but how many cycle, class? If we have 4 peaks. Class,
Is it
are you with me?
zero?
3 cycles. Okay, here to here, 1 cycle. You know what it means by cycle? Here to here, 1 cycle. Here to here, another cycle. Here to here, another cycle. So basically you have 1 peak to peak, 1 cycle, yeah? So 2 peaks, 1 cycle. So 4 peaks, you have to minus 1. That's why the equation is like this. N plus 1, because they know that you have always an extra peaks. So 4 peaks, you have 3 cycles. Are you with me?
Yes, madam.
Okay, very good. So then you have, what is your x1 value then? X1 value, can you see the value? Besarkan sikit. X1 value apa?
0.08.
So sini 0.08. Okay, maybe the last one, what is X4? What is X4 class? Can you see?
0.01.
Yeah. Halfway, right? 0.01. Okay, so the way you write the equation is 0.08 divided by 0.01, 0.693. Okay, so we haven't finished because they ask you to find C3, which is the new C, yeah? You remember, then you have to relate your equation with your zeta. You haven't finished because this is like when you change that to a different damper and you have this response, that means your zeta also change because your C, you put a new C into it, you have new C equivalent and you have new zeta. That's what it says here. So your zeta here from the equation based on logarithmic decrement. Look at your list of equation. Easy peasy. So if you substitute, you get 0.11. Okay, then what do we do to get C3? Okay, remember it's we are still looking at this equation. Okay, at this in this system, but now instead of C1, they change it to C3. So you can use this relationship for your C equivalent, but you change your C1 become C3. So your C equivalent, okay, first you write your equation of C equivalent related to your new C equivalent, yeah, because you have your new value 2m omega n zeta, because you zeta, if you substitute that, you get 24.1 Newton second per meter. And then you use this equation, but now with C3 and solve for C3. So your C equivalent is also equals to C2, C3, C2 plus C3. So no more C1. Huh? So you just substitute because you already have your C2 value. So if you substitute, then you solve for C3. So you get C3, just rearrange the equation. Okay, any question? Any questions so far? Wow, it's already 11:45. Class?
So far, no question, madam.
Okay, so roughly you can see that if you look at other example of tests, the midterm test as well, the questions are about the same. You know, we're gonna ask you, maybe we give you different system, but it's all related to the concept or idea of zeta. You know what happens if there's no zeta, or if there is a zeta, how do you actually write maybe or calculate the values, the response and the values of zeta. All right. Maybe we don't have time for this one. You can look at the